Yeah. Hi, Professor Burtsekas. Can you hear me? Am I audible? Can you hear me, Professor Burtsekas? Can you hear me, Professor Burtsekas?
Yes, I can hear you.
Okay, thanks. We'll get started. I'll first introduce you briefly and then we'll get started with your talk. Is that fine?
Okay, you give me the signal.
Okay, thanks a lot. So it's an honor to have Professor Dmitry Burtsekas from the Arizona State University. He taught for a very long time, almost 40 years at MIT. And he is extremely well accomplished, has received lots of awards and honors over a career spanning several decades. And he has written several important textbooks that are widely followed worldwide. Textbooks on dynamic programming, optimal control, optimization, convex optimization, nonlinear optimization, and so forth. We, in fact, follow a lot of his course material in the courses that we teach. More recently, he has been actively writing a lot of books on reinforcement learning. It's really an honor to have Professor Burtsekas with us. You can see the audience, I guess. And there are also people sitting on the left flank and the right flank, which probably you won't be able to see, but I guess you'll have an idea of how many people are there, and so on. People are still coming in, but I guess we'll get started with your talk. So let me welcome Professor Burtsekas let's welcome him with a wide applause. Over to you, Professor Burtsekas. It's all yours.
Okay, thank you very much, Shalab. It's my pleasure to give this lecture on computer chess and its relations to model predictive control and reinforcement learning. This is material that's based on my course at IISc, and particularly the last two books that I've written. One is already available on the internet and is about to be published in print. This lecture is also connected with a computer chess paper that I have written with two colleagues, Yuchao Li and Atharva Gundawar, and you can find it online. So let me give you the outline of what I'm going to talk. I'm going to discuss the relation between reinforcement learning and model predictive control, MPC. And I'm going to use computer chess as a vehicle for that. Then I'm going to discuss a theoretical framework for MPC that's based on Newton's method for solving the Bellman equation. I'm going to discuss first one-step look ahead and then MPC with multi-step look ahead. And then I'm going to come back to computer chess and how we can improve the performance of any given chess engine using model predictive control. So let me first talk about a remarkable computer chess program, AlphaZero, which came out a few years ago and created a great deal of enthusiasm for the prospects of reinforcement learning. Now, AlphaZero and most chess programs involve two algorithms. The first is the offline training algorithm, which trains a position evaluator using machine learning and deep neural networks in the case of AlphaZero. And this is the algorithm that whereby the program learns how to evaluate positions and how to play based on these evaluations. And then there is the online play algorithm that it used to play online with human and computer opponents. And this involves multi-step look ahead with a position evaluation at the end. Now, most attention has been focused on the offline training algorithm of AlphaZero, which involves some important innovations in deep neural network technology and other things. Now, the online play algorithm is more or less traditional, has a lot of commonalities with the algorithms that have been developed, the programs that have been developed in the past, and it's the one that's critically important for good performance. And also the online play algorithm in computer chess generally is strongly connected with MPC. So let me first discuss the MPC in a form that's convenient for the purpose of this talk. It's applied to discrete time deterministic optimal control. It involves a deterministic system where xk is the state at time k, uk is the control at time k, and the state evolves according to this equation. And there's a cost per stage, which depends on state and control. And MPC involves multi-step look-ahead optimization with cost approximation, a function j tilde at the end of the look-ahead. And in particular, at a given state xk during online evolution of the system, we solve an L-step look-ahead problem with a terminal cost function j tilde. The problem that we solve is the following. The cost function is the sum of the cost of the first L steps following stage k, plus a cost function approximation, which approximates the future stages and depends on the stage at the end of the look-ahead. So this is an L-step deterministic optimal control problem, which can be solved to give a sequence, an optimal sequence. We apply the first control in the sequence, u tilde k at xk, and we discard the remaining controls. And then we apply this control at xk, and then we go to the next state, xk plus 1, and do the same thing, and so on. So that is MPC. And now let me talk about computer chess in the online play algorithm computer chess. The chess position is the state in this particular case. It evolves over time. At the kth stage, we have a position. And here we consider all possible legal moves. This is the control that we apply. The opponent also chooses a counter move. And this is continued for several moves. And then at the end of the look ahead, we evaluate the position, back up the computations to the current position, and find the best move. So again, it is multi-step look ahead with a position evaluation at the end, like MPC. It's basically, this architecture is basically isomorphic to the MPC architecture, except that in chess, the state and control spaces are discrete, while in MPC, they are usually continuous. Also, in chess, the look-ahead tree is usually pruned. We don't consider all legal moves, but instead only the ones that seem most promising according to some criterion. On the other hand, in MPC, the look-ahead optimization is usually exact. And we're going to discuss this a little later, and this is going to be significant in what I'm going to talk about later. Now, these two differences, I will argue, are inconsequential, and our Newton step theory allows arbitrary state and control spaces as well as inexact look ahead. There's also another difference. Chess is a two-player game, while MPC involves one-player optimization. You can think, however, chess as a one-player game if you view it as chess against a fixed opponent. So we get to know the moves or predict the moves of the opponent, and then it becomes a one-player game. Now let me give a summary of the principal viewpoints of this talk. I'm going to argue that one online play with one step look ahead is a single step of Newton's method for solving the problem's Bellman equation. And there's a similar interpretation that applies to multi-step look ahead. And the offline training algorithm provides the starting point for the Newton step. The online play algorithm, however, is the real workhorse, and by comparison, the offline training plays a secondary role. Then I'm going to argue that the Newton step framework is very general because it's couched on abstract dynamic programming ideas, which allow arbitrary state and control spaces, stochastic problems, deterministic problems, hybrid systems, multi-agent systems, minimax, anything goes. This Newton step framework applies very generally. And then the other point that I want to make is that by using an architecture whereby we integrate existing chess engines, we can obtain favorable results. In particular, we can beat the engines on which are involved in our architecture. So the Newton theoretical framework for MPC, I'm going to explain this in terms of a visualization for linear quadratic problems. And I'm going to consider this is a very, very well-known framework, a linear system and a scalar system for the purpose of visualization. A and B are given scalars. The cost function is quadratic. Q and R are given positive scalars. And there are very well-known facts about this. The optimal cost function is a quadratic function of the state, and the optimal control policy is a linear function of x. And in particular, the optimal cost function is this quadratic, where k star is a scalar that's obtained as the unique positive solution of the Riccati equation, which is a fixed point equation with this Riccati operator given by this equation here. And the optimal policy is linear of this form, where L star is a scalar that's calculated in terms of k star by this formula. All of this is very well known. I'm giving it for one-dimensional problems. There are generalizations for multidimensional linear quadratic problems. And moreover, the insights that I'm going to give you based on this simple problem generalize very, very broadly. So let me illustrate graphically the solution of the Riccati equation. Here is k, the cost coefficient, and the red curve is the graph of the Riccati operator given here. To obtain the solution of the Riccati equation, we have to find a fixed point of this operator. So we intersect this red graph with a 45-degree line. We obtain this point here, and this is k star, the optimal cost coefficient. Let me also illustrate the value iteration algorithm, which generates iteratively the cost functions of k-stage problems. This is the cost function of the infinite horizon problem. The value iteration generates the optimal cost function of k-stage problems, iterates with a Riccati operator up until convergence to k star. Now, these k-stage problems have cost functions that are quadratic with a coefficient k of k, which is obtained by iterating like so, with starting from a given initial condition. And graphically, at the typical iteration, we have kk. To obtain kk plus 1, we go up here. And then we reflect along the 45-degree line, and this is kk plus 1. Then kk plus 2, and then kk plus 3, and so on. So the iteration is represented by this staircase evolution towards k star, and it converges to k star. Now, let's also look at the Riccati equation for linear policies. Let's consider a linear policy of this form. L is some scalar, and let's consider its cost function. It is quadratic of this form. KL is the unique solution of a corresponding Riccati equation for linear policies. It's also a fixed point equation with an operator f of L, which, however, is linear. It's linear in k. This is the coefficient of the linear term, and this is the constant. And the policy is stable if this linear coefficient is less than 1, and it has a linear graph like so. It slopes at an angle less than 45 degrees. But there are also unstable policies which have graphs that slope at an angle greater than 45 degrees. And so this is the Riccati equations visualization for linear policies. And now let's visualize MPC with one step look ahead. So we have this red graph here, which is the graph of the Riccati operator. And we have these graphs of the policies, which are lines. And all of these lines lie above the red curve, clearly, because these are suboptimal policies. And you can show rather easily that the graph of the red curve is the lower envelope of this of these lines. So we have all these lines, and some of them go down and touch this graph of the Riccati operator. If you take the lower envelope, you obtain the red curve. Now, let's consider MPC with a terminal cost function approximation that's quadratic with coefficient k tilde. How can we visualize that? Well, we go up here and we take the tangent line. This is the MPC policy for one step look ahead corresponding to k tilde. And the cost function of this policy is obtained by intersection with this 45-degree line. It's over here. So what we do to visualize MPC, we linearize the Riccati operator at k tilde. And then if we look at this graph here, we see that it's exactly Newton's method. In order to find the fixed point of a nonlinear equation in Newton's method, at the current iterate, you linearize the operator, solve the linearized problem, and then that's your next iterate. So MPC does one step of Newton's method starting from the cost function approximation coefficient. Let me also note that the concavity of the Riccati operator is also important for this figure to be valid, and it's important also for the more general theory that generalizes this figure. So here's another view of the Newton step. Riccati operator, cost function approximation, the MPC policy, and we obtain here the cost coefficient of that policy. And the Newton step takes k tilde into this KL. And the convergence, of course, of Newton's method is superlinear as long as you are within the region of convergence, which means that this error is tiny relative to this initial error. And that explains the good performance of MPC in practice. If you are within the region of convergence of Newton's method, MPC works very, very well. Excuse me. So then let's now look at the corresponding picture for multi-step look ahead. To understand multi-step look ahead, it's important to realize that it's really one step look ahead with a different starting point, a starting point that's obtained by applying L-1 value iterations to k tilde, or the cost function approximation corresponding to k tilde. So there's an initial step of the look ahead, and then the remaining L-1 steps, and then the quadratic cost approximation. But only the first step is the Newton step. The remainder just serves to bring k tilde closer to the optimal solution by means of value iterations. So in terms of a different kind of visualization of the Newton step, we have cost function approximation k tilde for two-step look ahead. We first apply a value iteration, and then we apply the Newton step. And that's what we obtain from two-step look ahead MPC. That's the two-step look ahead MPC policy. If we had 10-step look ahead, then from k tilde we take 9 steps, and then finally the 10th step would be the Newton step. So this highlights the importance of the first step of the look ahead. It's only this first step that's the Newton step. The remainder serves to bring the starting point close to the k star. So this can be done approximately, but this has to be done exactly in order to be an exact Newton step. So that's an important insight. The first minimization step should be done exactly, while the remaining steps can be done approximately. And this has far-reaching practical implications. I'll give you one example. In stochastic problems, for which this Newton step interpretation also holds, we can use certainty equivalence approximations for all the look-ahead steps except the first one. And this simplifies the computations tremendously, and also with relatively little degradation in performance. And this fact has been verified with computations over a long period of time, starting with my work with David Castagnon more than 25 years ago. And there are other contexts also where approximations in the subsequent steps of look ahead can be of important significance. So now let me go to computer chess using MPC. At IISc, we have done quite a bit of work involving discrete state and control spaces, combinatorial problems. I'm listing some of those here in collaboration also with Stephanie Gill. I'm excited about this work, which is very recent. It has to do with a Viterbi rollout algorithm, an algorithm that is a simpler version and far more computationally efficient than the Viterbi algorithm, and therefore applies to large-scale problems. But for now, I'm going to focus on computer chess. And we have an architecture in which we introduce existing chess engines for the purpose of playing better computer chess. So we introduce a one-player MPC architecture where the true opponent is approximated by a nominal opponent. In particular, this architecture involves two chess engines which are available. And these chess engines are components, so this is a meta algorithm that incorporates other algorithms into an architecture. The first engine is the nominal opponent engine. It's used to predict the move of the true opponent of that we're playing against. So instead of having a minimax player after we play our move, we substitute that with the play of a known engine. Then we have a second engine that evaluates the position at the end. And in this way, we have a Newton step starting at the position evaluation. And the calculations involved here are looking at all possible legal moves, then generate the predicted value of the opponent, and then evaluating the result and choosing the best move. So that's our architecture, and the important thing to note is that these evaluations can be done in parallel, and these evaluations can be done in parallel. So that's important for the for computational efficiency of the algorithm. And now let me give you some computational results that we have gotten using as nominal opponent and position evaluator the Stockfish engine. Stockfish is a well-known chess program, a champion program. It's been around for many years. It's used as a benchmark for evaluating other chess engines. And in these results, we have, that I'm going to show you, we have tested two variants of the algorithm, the standard version and another version, which we call fortified. And let me not explain what this is. It's a little more conservative, plays a little better against very strong opponents and a little worse against weaker opponents. And here are the results of some chess matches. We have our architecture, MPC-MC, that uses Stockfish engines as components, and we play them against Stockfish. And each one of these entries represents a 10-game match. We have tested against three Stockfish engines of different strength at half a second per move. This is a pretty good chess player. At 2 seconds per move, it's a very strong chess player. And at 5 seconds per move, Stockfish is almost unbeatable. It plays almost perfect chess. Now, the numbers here represent the score as customarily recorded in chess. 1 point per win, half a point per draw, 0 point for loss. So this means, okay, MPCMC has lost in all these matches, did not lose a single game. And in this particular match, it won 5 games and drew 5 games. In this match, won 6 games and drew 4 games, and so on. This involves a nominal opponent which is exactly known. This involves a nominal opponent for which some noise has been introduced. And you can see that for this weaker strength stockfish engines, we decisively win. And as stockfish becomes stronger, we have more difficulty getting an edge, but still we do get an edge. Of course, at 5 seconds, stockfish plays almost perfect. It's very hard to beat. We have also done a lot of tests with using weaker engines, Komodo Dragon, other engines, and we have obtained better results, actually. And we can also show better results with multi-step look ahead, although we have not done extensive tests in this regard. And as I mentioned earlier, parallel computation is essential in order to reduce the move generation time. So this gives you an indication of our results. To us, they were quite surprising, and it's worth asking why this is so. What's the reason? Now here, I can't offer you any assessment with certainty. It's only a speculation. Our consistent observation is that MPCMC improves the play of weak base engines decisively, and the play of strong world champion level base engines narrowly. And so why is this happening? After all, MPCMC looks ahead 1 more step. Chess engines look forward 20 steps, 30 steps. So we add only 1 more step of look ahead, and yet we're getting such an advantage. So we looked a little bit more into this. And one observation here is that MPCMC plays mostly the same moves as the base engine. So it replicates the moves of Stockfish, the engine that does the evaluations, plays the role of nominal opponent, but occasionally it varies in like 10–20% of the moves. Like once in every 10 moves, you get a different move by MPCMC, but oftentimes this is important. Sometimes the base engine misses some hard-to-find strong moves at the very first of look ahead. It prunes it out, thinking that they are not promising. On the other hand, MPCMC does not prune out anything. It has to do with the first step of look ahead has to be exact. No approximations in order to be able to replicate the Newton step. So that's where I think that MPCMC gets an advantage, and because it performs a true Newton step. Now, all of this is quite counterintuitive. Why the first step and not the subsequent steps? However, it's consistent with a lot of experience, it's consistent with theoretical insights, and with much experimentation with other reinforcement learning and MPC case studies beyond chess. So that's my final slide, and thank you very much for your attendance.
Right, thank you, Professor Bartsakas. We have time for some questions.
Yes, if you could speak a little bit more loudly.
Yeah, 1 second.
So, Professor Bartsakas, I hope you can hear me. Can you hear me?
If you could speak a little more loudly.
Professor Bartsakas, can you hear me now?
I can hear you, yes.
So my
Speak
question,
slowly and loudly if you can.
Yes. So you spoke about this multi-step look ahead. I wanted to understand in this game of chess, how challenging does the multi-step look ahead become as you start looking more steps ahead, and how do you deal with the challenges that result in this multi-step look ahead?
Well, our architecture and the results that I've presented use one-step look-ahead. With multi-step look-ahead, like two-step, for example, there's another layer, and it increases the computation, of course, but we haven't tested anything beyond 2 steps. And the generalization to multi-step look-ahead is straightforward. It's just that the computation increases. If you look at my paper, you'll see diagrams that explain the multi-step look-ahead.
And maybe a follow-up question. So in your calculations, do you work with function approximation, or in some sense you work with perhaps the tabular setting?
The cost function approximation at the end is provided by the stockfish evaluation. I'm not sure I understand your question.
Okay, maybe I'll look at your paper and then maybe get back to you. Thank you.
You also mentioned about the stochastic version of the problem. So do you look at maybe the RL version as well, or which means you just have access to data, you don't really have access to the model information?
I spoke about an approximate opponent, a stochastic opponent. Is that what you mean in the computer chess, or generally in MPC?
In generally, because you said the first step has to be exact, the Newton step.
Yes.
So the thing is, if you just have access to noisy data, I mean, how exact can you be?
Yeah, the first step is going to be stochastic. So if you have, so you have to take into account the disturbance, the stochastic disturbance in the system equation, in order to generate the set of all possible next states. In other words, from xk, you use the stochastic equation to obtain all the possible xk plus 1. And then when you do the subsequent approximation for subsequent steps after the first one, then you can use certainty equivalence. You can use a deterministic system to make your predictions forward.
Sure.
So that's where the savings come. If you have like 10 steps of look ahead, then the first step is stochastic. The other 9 steps are deterministic. So the look ahead tree is much, much smaller.
Sure. Okay. Thank you. Yeah. Any other questions? Yeah, one second.
Hi, Professor Bertsikas. When you presented the empirical results, you're playing against the stockfish base model, let's say. And is your position evaluator also the stockfish base model?
In the results that I have presented, we play against stockfish, and the 2 engines are also stockfish. The position evaluator engine is stockfish, and the nominal opponent is stockfish as well. On the other hand, this is not necessary. We can play against stockfish, the real opponent, and we can use a different nominal opponent, like Komodo Dragon, some other chess engine. And we can use a position evaluator that's still a third engine, a different engine. So in an actual match, there can be as many as 3 engines: the real opponent, the nominal opponent, and the position evaluator. And of course, the results depend on what engines you use and who you play. That predicts the value of the opponent is a fairly good engine. You cannot have a weak opponent and then make predictions, because these predictions are unreliable.
Thank you. Another follow-up question. This method is not particular to chess, so if you apply this to Go, you'll get similar results, I would think?
Absolutely. It applies to any 2-person game. Deterministic, however. It does not apply to things like poker or backgammon. It applies to Go. It applies to a Chinese version of chess. Any two-person antagonistic board game.
Thank you.
And we actually are trying to apply this methodology more broadly, but there are so many games, it's going to take us a long time before we exhaust them.
All right, so let's thank Professor Bertsikas. Thank you very much, Professor Bertsikas, for your excellent talk.
My pleasure. Thank you.
All right, so we'll have
Hello. So, welcome back to the second half of the first session today. We have with us Professor Martha White. So Professor Martha White is an associate professor of computing science at the University of Alberta and a fellow of the Alberta Machine Intelligence Institute, which is one of the top machine learning centers in the world. She holds a Canada CIFAR AI chair, a tier 2 Canada research chair in reinforcement learning, and has received IEEE's AI's Tend to Watch the Future of AI award in 2020. She has authored more than 70 papers in top journals and conferences, and her research focus is mainly on developing algorithms that learn to adapt continually with a focus on more sustainable systems. So today, she'll be discussing about better experiments in reinforcement learning. Over to you, Professor Martha White.
Thank you very much. It's definitely a pleasure to be here. It's going to be a little hard for me to tell for sure if you guys can always hear me, so I do hope that you'll interrupt if you need any changes on my end. So today, my goal is, this talk is a little less about giving you lots of new tools, new algorithms. It's more of a discussion about how we can run better experiments and some thought exercises around that. And then I'll give you at least a couple of references to some of the work that my group has done. But yeah, it's almost a little bit more of an educational talk. So I hope you'll enjoy it. So what is the thing that I really want to talk to you about today? So all of us here have done some research, and there's always different types of research you can be doing. It's easy to get excited about algorithm development. You come up with a new algorithm, you see it does better. It's very exciting. It's easy to get excited about big state-of-the-art demonstrations. When you can show that something that was not possible before is now possible is just inherently very exciting. But I think it can be harder to be very excited about rigorous empirical studies. And I think that sometimes makes its way into our work. And yet I think rigorous empirical studies are extremely important for advancing research in the similar way that theory is very important for advancing research. I think theory and experiments have very similar goals. What they try to do is they narrowly scope a question, and they really try to answer that question well in a very limited setting. And of course, you have to have a specific hypothesis that you want to refute or gain evidence for. So that requires a very rigorous approach, and it requires asking a very narrow question. So experiments are a lot more like theory than they are like engineering, where engineering, you get to show that you've solved something, you get to show a big demonstration, and you get to show that something maybe is even working in practice. But like I said, good empirical work matters a lot. So it's really important to understand our algorithms if we want to actually build on them. And if we don't have a solid foundation as a community, then we're not really going to be able to build on those algorithms. So today I want to try to convince you that we do have an issue here, and also that you should be very excited about empirical work. It's a very meaningful thing to do. I'll point out that a lot of this is coming from a recent long-ish paper in JIMLR, coming from my lab and Adam White's lab. He's a colleague that I work with often. And we think of it like an RL cookbook. It's a comprehensive guide to experiments, and it has lots of best practices, common pitfalls, lots of examples. So do go check out this paper for a lot more about how to do good empirical design and reinforcement learning. And I'm just going to sort of pick a few things from it as we go. Okay, and so generally the outline for what I'm going to tell you about today is more first about what some of the things we say in this paper. So we'll talk a little bit about a case study we went through where we tried to do our replication study and some of the things we learned there. And that I'll say some of the things that are in the cookbook. And then in the second part, I'll talk about something different than the cookbook, where I'll highlight that I think that we have a hyperparameter crisis in reinforcement learning, and is really leading to an important experiments practice gap. And here, when I say experiments practice gap, I mean we see lots of types of results when we run experiments in RL in our labs, in simulation. But when we actually want to bring those RL algorithms into practice, into deployment, there's a very big gap between what we see happening with our algorithms in experiments and in practice. And this gap is making it very hard to bring RL into the real world. Okay, so that's generally what I'm going to talk to you about today. And then I'll try to conclude that with some what I think are very important directions to try to fill this experiments practice gap. And in this workshop, I know I believe anyway, there's a lot of grad students and young students that are just getting started in research. So I hope for that to help you think a little bit about what you might want to work on. Okay, so I may be preaching a little bit to the choir here, but I just want to point out that maybe we see a lot of empirical work in RL, and maybe it seems like it's an easier thing to do, but good empirical work is very difficult. So when I say empirical work here, again, I don't mean demonstrating something's possible or doing an engineering demonstration. I really mean posing a specific hypothesis and then trying to either falsify it or gain evidence for it. So to do really good empirical work requires very careful design and rigorous execution. And at the same time, there's no procedure that you can just follow. Sort of just, again, like theory, where you can't just say, okay, I want to prove this theorem, and I'm just going to follow steps 1, 2, 3, 4, 5, and I'll be able to prove this theorem. It requires a lot of creativity, and you have to really think about how you're going to design good experiments. And in general, we just know this is true in all the sciences. The other sciences, like for example in animal learning, have to be very careful about how they design their experiments. So for example, if you are conducting eye blinking experiments with rabbits, let's say you're trying to understand how rabbits come to predict stimuli because you're putting puffs of air on their eye. Well, there's a little bit of an echo there for a second. Okay, great. It's been muted. Anyway, in order to run these experiments well, the researchers have to run several rabbits through the repeated trials of this experiment. And each time they do this, they have to be very careful about changing the conditions, like lighting, if they've handled the animals and made them stressed, if they're wearing perfume, etc. So they're really paying a lot of attention to how they run their experiments. So the good news for us is that experiments in RL are a whole lot easier than in the other sciences, and we should be able to do a much more thorough job. One of the reasons for this is most experiments in RL are in simulation. We get to completely construct the environment, the agent, and exactly the experiment protocol for that environment and agent. I will point out, of course, that not all experiments in RL are in simulation. People run experiments with robots. People run experiments in the real world. That's a whole other set of criteria to think about. So today we're just going to focus on running good experiments in simulation, since so many experiments are run in simulation. Okay, so the good news is in simulation, experiments are a lot easier than other sciences. And for a variety of reasons. We can control and isolate many sources of variation. If I want to compare and ablate agent 1 and agent 2, I can very carefully change pieces of it. We can measure many different things. We can run many independent trials and do these all in parallel. And we can do it on computers that are very fast. So these are all things that make experiments for us a lot easier. And yet, we still have some poor empirical practice. So I'm going to go through a case study that we went through and just draw some conclusions of why I think it's important for us to start trying to run slightly better experiments. And I don't mean to call out any specific papers here. I have lots of papers where we've done some empirical things that were not as rigorous as they could be, and I hope to be better each time. But it's good for us to sort of step through and try to do replication studies and see what goes wrong. Okay, so our goal was to reproduce a result from the literature with 2 well-known policy gradient algorithms. So here the result was particularly looking at SAC and DDPG, but in this paper they ran multiple other algorithms as well. We were just asking, could we recreate the result with DDPG and SAC? Okay, so this is this original result here. I hope you can see my mouse. And SAC is performing reasonably well. DDPG is doing pretty poorly. And we tried really hard. So Samuel Newman is the PhD student that was on this paper. He tried very hard for quite some time to get this to be replicated. He went and tried many more runs, tried to do hyperparameter sweeps to see if that was causing SAC not to perform well, and then tried many different architectures and different implementation choices for SAC to try to get this to actually match performance we see here. So there's a big gap. This is the number we get. SAC's actually all the way up here. Okay, and DDPG is also suffering. So why did this fail? Well, we started trying to dig deeper to understand why is it that we're having so much trouble replicating this result. First thing is we started digging deeper. We didn't know the repo had wrappers for 2 different code bases, so it was not clear which baseline was actually being used. Was a DDPG from this code base or was a DDPG from another code base? Neither paper nor the repo actually told us the hyperparameters for these baseline methods. And the repo code, as is typical, did include algorithm components that were not mentioned in the paper. So I'll just step through some of these. First, a couple of things that we noticed is that there seemed to be a lot of variability across runs. So some runs were very good, some were very terrible. So we thought maybe it's that they got lucky seeds, or maybe they intentionally chose seeds that were better. We did notice the code had an option to search for good seeds so that they could actually get good seeds. Now, this is a little bit uncharitable, but that was one of our hypotheses. And then another possible culprit was that we noticed the code had an undocumented choice of an initial expiration period. So this SAC algorithm would randomly explore for some number of steps, and then it would actually start doing updates. That wasn't in the paper, but it was in the code. Okay, when we actually went and added those to what we had, we found that either of those things could have actually solved the problem. So this was SAC, where we did a seed search. So that means that we went and tried to actually get, if we had to pick 5 seeds, we picked amongst the 5 best seeds, we could get good performance. And then if we also added this exploration phase, we also managed to get that performance to come up as well. And now it's matching pretty closely to SAC. Okay, so at this point we've decided, okay, it's probably not the seed searching part of the code, it's probably the fact that this initial exploration was important. Okay, and then at the same time, we're going to dig deeper and see if we can actually get the baseline to do better as well, since we had to make some changes to our own to get it to try to match their performance. Some of the first things we did is just get better hyperparameters and change a little bit about how action selection is done in DDPG. And we also noticed that there was an error in how the episode was cut off for DDPG, so we changed that. And then finally also added the same exploration phase. Okay, and now we found that DDPG could perform a lot better than before. So it's still worse than SAC. There's still a gap here, but quite a bit better than it was reported in that paper. Okay, so these conclusions from this study, and what are we actually drawing from this study? The first thing I really just want you to take from this is we were able to get eventually to somewhat similar results to the previous paper, although some important differences. But this took actually quite a lot of effort, a surprising amount of effort. And so the inability to replicate this made it really time consuming to build on. So if you want to build on things from someone's paper and it's hard to replicate what they've done, it's really hard to build on their algorithms. Another interesting thing was this undocumented choice of exploration was actually really important. The paper actually could have focused a bit more on this. This insight, I think, would have been very useful to investigate more. Another insight here is, I guess, DDPG was actually not doing that poorly. And of course, all these experiments, we saw lots of variability across runs. Okay, so yeah, this is relatively representative of our papers. There's all these different choices you can make. It's hard to replicate some of these results. Now let's just start looking a bit more deeply into how are we going to be more rigorous and what does that actually entail. So why do we have so much variability and why is it so hard to actually get good empirical work? If we, for example, take a pretty typical learning curve of one of our algorithms, DQN, on a pretty simple environment, mountain car, and we average this over 200 runs. If we actually go, because so here this is average over 200 runs with 95% confidence interval. I mean, it kind of has a weird dip here, but it does learn. But if we actually go and look at any individual run, each individual run has highly variable performance. So these blue lines here, this is what one run looked like, this is what another run looked like. So on average, our algorithm looks like maybe it's reasonable, but it can be extremely different across our different runs. And so again, no wonder we have so much variability, it's hard to replicate. And some of the ramifications of this variability is that it's really hard to make very strong conclusions and we might be misleading ourselves. So we ran an experiment where we imagined that 10,000 labs were trying to run the same RL experiment in parallel, and all of them are trying to rank 4 algorithms using as few seeds as possible. Because we always want to use as few runs or few seeds as possible because it's so expensive to run all our algorithms. And now how many seeds would we actually need to be able to say, I confidently ranked my 4 algorithms? Okay, so the way we simulated this is that we generated many, many runs for all these algorithms, and then we subsampled for each lab, and we did that 10,000 times as if a different lab had seen a different set of seeds, and then we saw what ranking they got. Okay, it's a somewhat complicated meta experiment. Okay, so this is the results that we got from this paper at RLC last year. And this is saying if we just took 3 runs to rank our algorithms on these relatively simple environments, on Acrobat, 47% of the labs would have concluded the ranking incorrectly. CliffWorld, 54% of them would have concluded the ranking incorrectly. And so that's a lot of labs getting the wrong ranking. If we move to 10 runs, 10 seeds per environment, now it's starting to get a little bit better, but still quite a lot of incorrect conclusions. And then as we start getting to the 30s, it's getting a little bit better. These ones are getting better. And as we have 100 runs, each lab gets pretty confident that it's actually got the ranking correct. Okay, so this is something that should be somewhat concerning because it means whenever we run an experiment and we only use 3 runs, then we might be one of those labs that just concluded incorrectly that we had that algorithm 1 was actually better than algorithm 2. And just giving you a few more examples of what these performance distributions can look like when we have a small set of runs. If we take an algorithm like Sarsa Lambda tile coding on mountain car, again, these results are in that cookbook. this is what our runs might look like. It's very hard to draw any conclusions about what the distribution over runs looks like. If we start adding more runs, it's still really hard to judge exactly what these distributions are. As we start getting 100 runs, maybe it's starting to look a little bit Gaussian-y. Maybe in here now we're really starting to see what this distribution looks like, and there's a bit of a skew to this distribution. Okay, so we're often reasoning with just samples that look like this from distributions that actually look like that. Even more common is to have high bimodality in our results. So here, if we take DQN and we run it in cartpole, again for let's say 200 runs, and then we actually plot what the performance looks like across those runs. For some of the runs, the agent balances only for 35 steps. So for a bunch of the runs here, it's only balancing the pole and cartpole for a small number of steps. Sometimes it's very good and balances for a large number of steps, but very few agents actually balance for 125 steps, which is what the mean performance is that we end up reporting. So we end up suggesting that DQN can balance the pole for about 125 steps, but is actually really behaving much more like these two modes. And even more so, that bimodality happens at some point in the learning. These curves can also look very different throughout training. So these distributions can be quite complex, and it's not just that we have bimodality in cartpole. We have bimodality that changes throughout the learning of this agent. It's a fun animation. Okay, so mainly my main point here is that the behavior of these agents is quite complex. We can have quite a bit of variability across runs, and the only real answer to this is to try to look more closely. This might mean doing a few more runs, actually looking at individual runs, and really trying to understand what are our agents doing. And in general, we want to do this not because we want to make very strong claims, but whenever we run our own experiments, we always want to avoid misleading ourselves, because otherwise we're wasting our time. So that's sort of why this section is called Part 1, Don't Waste Your Time. Is that running bad experiments is just a complete waste of your time, because you didn't get that insight that you wanted. You just got a result that doesn't give you a clear conclusion. And so we always want to ask ourselves, what is the true outcome here? Because we don't want to mislead ourselves. A very natural reaction to this is the what if, so there is a lot of variability here, but it's very expensive to look more closely. So this is a very, very common question that I just want to react to. Do I really need more runs? So it's a very common reaction to say my agent and environment is huge, and I really cannot do more runs. It requires too much compute. So I totally understand this reaction, but I just want to translate what that reaction really is. What you're saying is, I want to run an experiment that I don't have enough resources for. So can you pretend with me that my result means what I claim it does? Well, that's not very useful. You don't want to pretend something is true. You want to know that it is true. So the alternative there is not to run more in this very expensive regime. You have to actually just start becoming more creative about asking empirical questions where you can actually get the data and have the compute to answer it. So one very basic creative solution to this very common dilemma is to start trying to think about, if I want to make strong claims, I need to try to aggregate across environments. So often our papers will have many different environments, but maybe a very small number of runs or seeds per environment. But once you start aggregating it across all your environments, you might actually have a compelling story that this algorithm is truly better than that algorithm. So there's different nice normalization options out there to try to aggregate across environments. And now we can really be rigorous across environments. And now we just shouldn't say anything too strong per environment. If I have 5 runs in an environment, it's hard for me to say one algorithm is better than another. But qualitatively, I can actually look at each individual run and start to learn something about how our algorithms behave. So this is a way to say, okay, we have a limited compute. What's something that we can do that's rigorous but still informative? Okay, great. Okay, then the last piece of advice when it comes to how are we going to start running experiments better. So far what I've told you is we have some issues with trying to do replication of existing studies. We do have some needs to be more rigorous in our studies. Part of the reason for this is because there's just so much variability in RL experiments. So I hope I've convinced you that we can have very significant differences across runs, and we can make wrong conclusions if we don't have enough runs to characterize our distributions. And so I'll just give you one final piece of advice about how to run good or better RL experiments. And I'm just going to distill that down into rule one. I think this is almost always the question that I come back to about how do I make good empirical choices. So often when we're working on a paper, we'll come up with a new algorithm and we'll ask ourselves questions like, do I have to compare to PPO, which is a very common algorithm used? Or do I have to ablate this choice in my algorithm? In general, do I have to do Y? Okay, and the answer to this is always think about the problem you're solving and if that empirical choice is actually sensible for that problem. So rule one of all good empirical design is just to be very clear about what problem you're solving. And if you know exactly what problem you're solving, you can know what experiment you want to run in order to understand that problem. So I'm going to go just through a couple of thought exercises on this and highlight what I think are the key problem settings in RL, and then go through some thought exercises with that. So to me, there's really three key problem settings in RL. One problem setting is solving simulators. So that means I want to go find the optimal policy given I have a model or given a simulator. So given a model or simulator, go find the optimal policy. This problem setting is not as interesting to me. It's not the one that I work on as much, but there's some interesting use cases for it. For example, in the real world, engineers will often use models to better understand their systems. Like if they have a wastewater treatment plant, they might actually build a model of their wastewater treatment plant and then try to compute good policies in that model or in that simulator. And then they're not going to actually deploy that policy. It just helps them understand how their wastewater system works. And then another more recent use case is looking at really big search problems, say ones like for chip design or drug discovery, and then solving those simulators to solve those problems. More common, though, I think in RL is that people have usually thought of as these two, that they're working on these two problem settings. So the online RL setting is how do I get my agent to learn while it's in deployment in the environment? I'm going to include inside this offline to online RL, also called hybrid RL. So online RL, learning and deployment, and then of course offline RL, just learning from historical data, where that data might come from some unknown policy, and then we're going to deploy a fixed policy that was learned from that batch of data. And somewhat related to that is sim to real, where you learn a policy offline in a simulator, and then you transfer it online. So there's still sort of this transfer of a fixed policy. Okay, but I'm still going to categorize into these three. This is the interactive component of the talk. I was kind of curious from the audience if this would be possible, but if you could tell me what problem settings that you're interested in. So maybe it's all of them. I'm not saying you have to pick one, but maybe I can get a show of hands. Who in the audience is they're primarily interested in the solving simulators problem setting? I'm curious how many hands I'm going to get. Okay, who in the audience is the most interested in the online RL setting? Okay, great. Yeah. And then how about the offline RL setting? Okay, neat. Yeah, so quite a lot of interest in the online and offline RL setting. Okay, great. Those are the settings actually that I'm very interested in as well. And so this is where I'm going to again say that sometimes I feel like we're not designing our experiments to really target these settings. Let's just go through a thought exercise about how you might answer some empirical questions around these two settings. So let's imagine you're introduced a new variant of soft actor critic. You want to say my new soft actor critic algorithm, let's call it SAC plus, has state-of-the-art performance in half cheetah. That's an environment from a suite called Majoko. And so you want to compare it to a commonly used algorithm like PPO. Okay, and now you ask yourself, all right, do I have to compare to multi-stream PPO? So PPO can run with multiple copies of the environment in parallel, even though my SAC plus algorithm does single stream. So we can only use one copy of the environment. Okay. This is not that hypothetical of a question. I've heard this question from my own students, for example, when we're designing our experiments. So hopefully you're thinking to yourself, okay, would I have to compare to multi-stream PPO? This is always going to go back to rule one of experiment design. So what is your problem setting? If your goals are to understand how am I going to develop algorithms to solve simulators, then absolutely you probably have to compare to multi-stream PPO, because that is a perfectly valid algorithm to use to solve simulators. And if someone else could use multi-stream PPO to solve your simulator, why would they use SAC plus that is a single stream algorithm if it's not better than multi-stream PPO? But if you're in the online RL setting, well, then you can't run multi-stream PPO. You don't have multiple copies of the environment. PPO is not runnable in that scenario. So then, of course, you don't have to compare to multi-stream PPO. It's not an algorithm that could be used for your problem setting. And so you can go ahead and run single stream PPO. Okay. I know a pretty basic thing, but it's going to be fun to keep coming back to rule one. So let's agree. Okay, great. We're interested in RL. Phew, we don't have to compare our beautiful new algorithm SAC plus to multi-stream PPO, because multi-stream PPO would win, and we don't want multi-stream PPO to win. So now we have to only compare SAC plus to single stream PPO. And when we do that, we have to decide what we're actually going to report for our algorithm. Okay. What I would usually report is reporting online returns. And that means as SAC Plus is interacting in half cheetah, you're going to look at the returns that it actually gets during learning. So, within the first time step 1000, you're going to go see what was the return for the agent that it got during the episode that happened on step 1000. You're going to plot all the returns that you actually saw, and then you're going to average all those things across multiple runs. So those are the returns you saw whilst actually learning. But one thing you'll notice in many papers is that what actually most papers do instead is they do offline rollout evaluations of the policy every 1,000 steps. So what that means is as SAC Plus is learning, every 1,000 steps, it's going to pause. It's going to take the policy that SAC Plus currently has. It's going to freeze it. And then it's going to do, let's say 30 rollouts. And it's going to see what was the expected return under that policy. And then it's going to plot that. Okay, so you notice that everyone does these offline rollout evaluations, and so you might think to yourself, okay, well, do I have to do that? Okay, this is the last one of these sort of very educational slides. And of course, I'm going to say the same thing. What is your problem setting? If your problem setting is online reinforcement learning, which I think we just said it is, it doesn't make actually a lot of sense to do that. So I know it's very common to do in papers, but it doesn't make sense to report offline rollouts if your online performance matters. It only makes sense to report offline rollouts if all you care about is the final policy. But in online RL, we actually care about the reward that our agent receives while it's in deployment. So we want to receive the rewards that it got while it was learning. Okay, fun. All right, that's all I wanted to say about how we're going to do better experiment design. Let's move on now to talking about what I think is at least one key experiments practice gap. Okay, and that is all related to hyperparameters. Okay, and I'll tell you a little bit about some of the things my group has been doing around dealing with this problem. But first, I'll sort of just emphasize what I think what this problem is and why I think it's such a huge barrier to deploying algorithms in practice. So hyperparameters in RL, I think we all know there's lots of hyperparameters in our algorithms, and it makes them hard to use in general. But for example, in DQN, there's all these different optimization parameters. There's all these different exploration parameters, like what's the minimum epsilon that we're going to use for epsilon greedy? What's the decay schedule around it? There's of course many different architectural choices. For weight initialization, we might try different strategies like inducing some level of optimism, and of course replay parameters. There's a large number of those. So we sort of take this for granted that we have all these hyperparameters, but it's quite large. And it can matter a lot what the hyperparameter choice is. So I'm showing this result from, again, this is actually my colleague's paper, Adam White and Michael Bowling with their student Jacob. This was just published in NERPS. And I think they have a couple of really beautiful plots around the hyperparameter crisis. And so this is a plot of performance of PPO, and it's showing performance in swimmer and in half cheetah. And for the exact same hyperparameters, it has really awesome performance in half cheetah, but does not have very good performance in swimmer. Okay, and this is showing performance across many different hyperparameter choices with many, many different runs. Okay, so this is problematic. And also a very nice plot from this paper is that in general, we can see a proliferation of hyperparameters in our RL agents. So as time has passed, our agents aren't getting simpler and easier to use. Actually, they're getting much more complicated. So, here in 1983, our algorithms had very few hyperparameters. Maybe they had the step size and the trace parameter. And as time has passed, we're seeing this exponential blow up of more and more hyperparameters being added to our very complex agents. Good. So the experiments practice gap here is that because we have, we had these hyperparameters, but in simulation, they're not really that big of a problem. So in the background, we can do a bunch of hidden tuning in simulation, You can sit there at your computer and try tuning a bunch of these different knobs, or you can do it systematically using a grid search or Bayesian optimization. But because you have this opportunity to do all this tuning of these knobs, that means you can actually get better performance in your experiments, and you're incentivized to add more hyperparameters rather than to remove more of these hyperparameters. So the fact that we allow hidden tuning in simulation has this phase where we really encourage the increase in the number of hyperparameters. But that means that we're not developing algorithms that are actually suitable for practice, because more hyperparameters is not good for practice. It is worse. Okay, and let me again just remind you why that is, going back to the problem settings we care about. So I care a lot about online and offline RL. In the case where you have a simulator, it's maybe not as big of a problem that we have all these new hyperparameters, because we can turn to auto RL algorithms like Bayesian optimization algorithms. There's these packages out there like Optuna and so on. So there, at least we can go and set these hyperparameters and maybe solve those simulators more effectively. I will point out, though, of course, even in this case, hidden tuning can be misleading, because if you introduce algorithm 1 with more hyperparameters in your paper, and it's better than algorithm 2 in that paper because you did hidden tuning, now if someone takes your algorithm and has to tune those hyperparameters using AutoRL for their simulator, in the end, they just want a policy as fast as possible. And if you have many more hyperparameters, the AutoRL plus your algorithm might be much slower than algorithm 2 with AutoRL. So even when we're solving our simulators, we should be accounting for our hyperparameters, but at least we can tune for them. We have a strategy. When it comes to online RL, how do we tune our hyperparameters? And when it comes to offline RL, how do we tune our hyperparameters? So these are two, I think, of the biggest open questions in RL. How do we pick our hyperparameters? Let me just tell you one of my own personal motivations for this problem. So in the last few years, I've started working on an actual real-world problem. It has been a great problem that we've looked at is using reinforcement learning for optimizing operation of a water treatment facility. So this facility, that water comes into a big tank from a river, chemicals get added to this tank, and that water is mixed to cause the organics to clump, and then they get pushed through filters that are in these orange, yellowy areas. And then periodically those filters have to be washed in a phase called backwashing, and that has a bunch of different control variables. So all these things are different actions the agent can do. It can change chemical dosing, it can change how mixing is done, and our goal was to adjust all of these in deployment, in real time, in order to save chemical costs and save energy costs. Okay, and so one of the very first things we do when you want to start deploying here is you ask, okay, well, what algorithm should I use? How am I actually going to deploy it to this facility? And hyperparameters becomes one of the biggest barriers for actually getting algorithms to run on these systems. So how are we going to run, for example, our SAC algorithm or something like that? We can't actually we cannot try many different hyperparameters. This is a real system producing drinking water for a town. So we can't just start experimenting with many different hyperparameters and either cause some damage to the system or just cause it to not be performing very well, and in the end cost that town more money because we increased chemicals or increased energy costs. So we can't just willy-nilly start trying many different hyperparameters. We cannot use default hyperparameters, and in fact we have found in general in our own experiments, if we take default hyperparameters for many of these algorithms like SAC or PPO, and we try them in very different benchmarks, they no longer perform well. And that's even still in simulation. So if we were to take those exact same hyperparameters and just try to deploy them on a real system, I would not be comfortable doing that. So our algorithms right now are tuned for our very different benchmarks, and they don't actually have true defaults that can be used for any problem. And then otherwise, we do have historical data for this problem. But even here, the same reason why offline RL, it's hard to tune hyperparameters, is actually a very hard problem to figure out how to use historical data to tune hyperparameters. I train with these hyperparameters, how well am I going to perform in test? We just don't have that in reinforcement learning because our historical data is often very limited, and you want to ask counterfactual questions about a policy that was never used to gather that data. So it's a much harder thing to do. I will point out that we've tried, or at least trying some simple ideas, again, inspired by this water treatment problem. And so we have this TMLR paper that's looking at how could we use just historical data to try to start tuning hyperparameters for an agent that's going to run online on a system, so in deployment. So yeah, if you're interested in checking that out, that paper also talks about some of the other work that's trying to address this as well. And there's not that much. Okay, so yeah, to me, there's a large hyperparameter crisis in our experiments and making it hard to actually move to practice. Let me now tell you, I've left quite a bit of time for questions. Let me tell you what I think are some key research questions to fill this gap. Okay, so I think one of the most important research questions here for specifically around hyperparameter selection is how to do better model selection in offline RL. So model selection here typically means policy selection. So if I give you a big historical data set, you're in the offline RL setting, and you use one algorithm to learn policy 1, and then you use another algorithm to learn policy 2, how do you know that policy 1 or policy 2 is better? Okay, so that's the model selection problem in offline RL. What you might want to do is might just want to do policy evaluation. You're going to say, okay, I'm going to hold out some data, or I'm going to somehow have data, or I'm going to evaluate policy 1, I'm then going to evaluate policy 2, and I'm going to see which one has a higher value. Okay, but unfortunately, there's a lot of known hardness results around how hard it is to actually do effective offline policy evaluation or off-policy policy evaluation, because our data sets need to have very good coverage to have good policy evaluation. But most real-world data sets do not have good coverage. So for example, in that water treatment scenario, the operators are not changing things very much. They stay in a very narrow regime, because if it works, they're not going to touch it too much. And that data would not be very helpful for evaluating a policy where we've tried to greedify, make it a better policy. It would probably produce a very poor evaluation estimate. So in general, this is just well known to be a very hard problem. I'll point out this in progress work with my just graduated PhD student about when can we know that offline policy selection is sample efficient for reinforcement learning? The answer is that in general, it is not. We know that it's a hard problem, but then there's some experiments trying to understand which algorithms seem to be better for doing policy selection. We also have another paper that says, well, if in general offline RL is hard, well, then we have to make some assumptions. So a very common assumption in the literature is to make assumption about the data, that you have particular data coverage. In some cases, that's just not going to be possible. So we went the other direction. We said, well, what if we made some assumptions about the actual MVPs themselves? And we had very nice structure in our MVP. So we looked at the special case of exogenous MVPs. Okay, and an exogenous MVP is one where you have a part of the state that you have no control over. You have no impact on it whatsoever. And then you have one part of the state that's endogenous. That's the part that you have impact on. So a very canonical example of an exogenous MVP is the stock market. The stock price, you have no impact on the stock price. So that's going to evolve however, whatever you do, it's going to be exactly what it was that historically. The only endogenous part that you have control over is your own amount of money and the own amount of stock that you have. So you can always counterfactually go back and look at a historical sequence of stocks, and you can answer a lot of counterfactual questions about what are all the different policies I could have run and how much money could I have made. So you can kind of get a feel for why this exogenous structure is very helpful for off-policy counterfactual reasoning, and that's why it's also very helpful for offline policy selection. Okay, so for that paper, we actually have an algorithm for selecting hyperparameters for our offline method, and it performs very well. Actually, I'll say one more thing about this, that this is another case where because offline policy selection is so hard, and because we're still doing all our experiments in simulation, for a lot of papers out there that use offline RL algorithms, there's a tendency to tune hyperparameters in the simulator. So like you train your policy offline, maybe you have to pick a particular hyperparameter, but then you'll just go check if I deployed this policy in the simulator, which hyperparameter would have given me the best policy. Now, I sort of understand this tendency because it's such a hard problem to pick hyperparameters. We might just want to know, could my offline algorithm work well? But again, it's not forcing us to realize that we don't have deployable offline RL algorithms if we don't have a way to pick their hyperparameters. Okay, so for me, I think this was an important realization for us that if we want to do effective model selection in offline RL, strictly offline RL, where you have to deploy a fixed policy, then we need to consider what MDPs is this even possible for. We looked at this one class of MDPs. I think an important question is what other MDP structure can we exploit to actually say we can say one policy is better than another policy and we can actually deploy the right policy. Okay, so that's essentially the hyperparameter selection problem in offline RL. And now we'll just reveal some of the other problems I think are really important. Obviously, I think developing algorithms with fewer hyperparameters is important. So like I said, we're escalating hyperparameters, and we really need to start thinking the other way. How can we get simple algorithms that are very easy to use? Maybe they won't be as optimal because you can't tailor them to each environment, but they will be much more usable. So, an example here might be to look at meta-learning algorithms that start setting these hyperparameters in smart ways, and they themselves might actually have reasonable defaults. We saw that for a lot of these algorithms, there's very different behavior across runs. So this is moving a little bit beyond hyperparameters and just thinking more generally about the experiments practice gap. Our experiments give average learning curves. It looks like our algorithms are doing reasonably well, but any one of those runs, if you had to run that on a water treatment plant, you probably wouldn't be very happy. So I think another really important experiments practice gap is to start asking how can we get more consistent and stable behavior across runs. We want our algorithms to not just be good for 5 out of 10 runs and then on average be okay. We really want them to be good for each of these runs. And we want to understand why they are sensitive. Okay, and then as a big part of that, if we want to start deploying these algorithms in practice, we do need to start understanding our agents better. So we need better tools to actually look inside our RL agents and understand what's going on. So understanding properties of the networks that we learn, understanding how much policies change. This, I think, is actually pretty in its infancy in RL. I think it's a bit more mature in deep learning. And I think there's a lot of very specific things that happen in RL that are different than deep learning, that there's just a lot of research that can be done there. Oh, sorry. So I'll mostly be concluding here. I'll just give you the key take-home messages. So experiments are important, but they're actually quite hard to do. It takes creativity and experience to design and conduct good experiments. A key thing about it is, of course, attitude. We always want to be asking, you want to dig deeper. You want to be unsatisfied with your own experiments. You want to only get satisfied once you get clear answers. For experiments, I think there's mainly one rule you need to remember if you want to run good experiments, and that's just to be very clear about the problem you're solving. Because if you always keep the problem in mind, I'm working exactly on online RL with these kinds of computational restrictions because I want to run it on these types of problems, then it'll always be a lot easier to answer what experiment you should run. So if you find yourself asking, do I have to do X? Then you go see rule 1. I think there's an experiments practice gap because we forget our real problems. So we forget that we want to use these RL algorithms to solve real control problems out there. And so then sometimes if we're forgetting that, we're not actually designing the algorithms that are going to be useful for those problems. And finally, the overall theme here is it's worth your time running good experiments. It prevents you from wasting your time misleading yourself and wasting your time working on the wrong problem. And your time is precious. As a community, we all want to be working on the most impactful things now so that we can be building together. Okay, a lot of this work was done with the great group at the University of Alberta and RLAI. This is a large number of students and faculty. And otherwise, thank you very much. And I'll keep it on this slide.
Thank you, Professor Martha White, for this very insightful talk. I'm sure each one of us has run into the kind of issues that you have highlighted, in particular, getting similar performances that have been reported in other papers. So hopefully we can take the message that was given by Professor Martha White and, ensure that our experiments are also up to standard. Okay, so now we have time for several questions now. So please let me know if you have questions.
Yeah, thank you. I have a couple of questions. So first one, you mentioned something about the lucky seeds as a culprit. So what do you mean by that? Does it refer to seeds where you have a subsequence of random numbers that are repeating itself, or is there any special structure that you are referring to as a lucky seed? And the second question is, Yeah, okay. Sorry. The second one is when you refer to the auto RL, are you referring to the like running RL layer above the RL layer on hyperparameters over the RL problem, or it is like the outer loop is like any sort of general gradient descent kind of setup? Yeah, thanks.
Gotcha. Okay, I'll answer those in order. When I meant the lucky seeds, all I meant was that if we look at these distribution of seeds, I know this is not actually the SAC result. I just meant that if you randomly took 5 seeds from these plots, it's possible that you could have randomly collected a few seeds from over here, and you could have just luckily gotten good performance for SAC and poor performance for DDPG. So my claim there was just, we were wondering if, because the distributions are so variable, that 5 runs really was skewing that result a lot just by accident. So this is a statistical claim. It's always possible with a small number of runs that you actually end up being an outlier, and that maybe was what was happening. So that's what we meant there. Hopefully that answers your question. And the second point about AutoRL, what I meant about AutoRL was largely these packages that are about using Bayesian optimization, or algorithms that are like the Bayesian optimizers, where what you have a bunch of hyperparameters, and then a Bayesian optimizer is going to solve sort of like this black box optimization problem. So it is not using gradient descent, because in many cases, hyperparameters, we don't have a loss surface that is differentiable. So instead, you'll do these Bayesian optimizations where you're going to sample different possible hyperparameters and slowly start narrowing a distribution around the optimal hyperparameters.
Yeah, so one naive question is like, one of the hyperparameters is the number of neurons and layers, right? If that is the case, like the more the neurons and more the layer, the performance is better. Like it's like, then in what way the auto RL helps here? Like the constraint will be the computational constraints, or anything else?
Right. I totally get your point there. Okay, yeah, that's true that the AutoRL community can also mean, for example, some of these like architecture search strategies. Here I was largely thinking about the AutoRL groups that are looking more at tuning some of the other hyperparameters. But maybe what I should say is I don't know what it means. I guess I don't mean to say that AutoRL solves this problem. What I wanted to say is just that whenever we have our algorithms that have a bunch of unspecified hyperparameters, in some sense, they are not fully specified algorithms. Like they're not actually algorithms. But if you layer an AutoRL algorithm on top, you could hand that to like a chemist, for example, and now it's a fully specified algorithm, and they can just run it on their simulator without having to know that bigger networks are better and that alpha should be equal to this and so on. So in that sense, AutoRL plus an algorithm that's unspecified because it has too many hyperparameters is a usable algorithm on simulators, but is not a usable algorithm for a practitioner trying to tune RL, to get an RL agent working for a water treatment plant.
Okay, yeah, thank you.
Hello, Professor. Thank you so much for your talk. I had I just wanted to know your thoughts about like solving simulators as one of the RL problems. How do you think about how interesting will it be to use that to understand or enhance explainability of the models that we are creating and deep learning, or the interpretability of them? And also, like going further down the line, how do you think we can improve our understanding of biological learning or neuroscience using this paradigm? What are your thoughts about that?
Okay, well, I definitely don't have a lot of thoughts about the second one, about how we can use simulators to understand biological learning. But maybe there you're imagining we could actually simulate processes in our brain, for example, and then try to use that to better understand ourselves. Right. Is that what you're thinking for the second one?
Yeah.
I think the use of more and more complex. Okay, actually, let me say my only opinion about the topic. Again, I do not know that much about simulators. Is that the other sciences have amazingly interesting simulators, like big simulations of weather, or even actually engineers have very complex and expensive simulators. So I think there's a lot that reinforcement learning can bring to those people, because those simulators are very expensive. They're so expensive that it's almost like you're interacting with the real world, because each sample is so important. So I think the tools we have in reinforcement learning can really help those with big complex simulators to, for example, find optimal policies where before they didn't have good algorithms to do so. So I see a lot of opportunity there, even though, like I said, it's not actually a problem setting that I work on that much.
Right, and about the explainability of models.
I mean, I don't fully understand that question, but if I do think that we're going to need to continue running most of our experiments in simulation where we can really probe and try different, say for example, variants of our algorithms to understand why does there sometimes happen to be a collapse? Why does sometimes sparsity emerge? So in that sense, I think simulations are very important for understanding our algorithms and therefore getting explainability. If you mean it in a different way, like you train a policy, Google trains some kind of policy, and then now it wants to explain that policy to the public, and it uses a simulator, then I'm not exactly sure what you're talking about
Right.
there.
Thank you so much.
Yeah, hi Professor. I have one question that as you have shown that if we change the number of seats, then result will get changed. So what could be the optimal number of seats? How we can decide that? And another follow-up question is that, like, we need to change the neural network architecture or the learning parameters across the RL environments or across the different RL algorithms. So how we can like generalize it? How can we just define generalized settings across the environments or across the algorithms?
Okay. Yeah, for the first one, I mean, fortunately, statisticians have answered this for us to some extent. There is a suite of different statistical tools to try to say, do I have enough runs or trials to say, for example, that this is actually different from that. So the paper does go through different confidence intervals and stuff, but there in general, it's going to be your statistical tools to say whether something is different or not. And it's going to be problem specific depending on how much variability you have. I hope that answers that question. Maybe you had more there.
Yeah, okay, thank you.
Okay, and the second one, the second part of your question was, how can we actually make our algorithms so that they have more consistent behavior with the same parameters across environments? Is that what the question was?
Yeah.
Okay.
So like I have seen like in simulation we need to change the neural network architecture, or like we need to change the, let's say, learning rates and other parameters when we like want to run the same RL algorithms across the different environment, let's say mountain car or cartwheel. So how can we set a generalized settings across the environments, RL environments? So that's my question.
Okay, so how can we get general settings of, for example, the architectures or the step sizes or something, some generic way to set these values across these different environments?
Yes.
Okay. I do think it's impossible to have one setting that works for all problems. Like it's unlikely that we can find one algorithm with one set of hyperparameters that's going to work for every problem. So I do think we're going to have to start better understanding when we have problems of a particular type, let's say like low dimensional, non-image based, have timescales of this type. This is when these algorithms perform well with these hyperparameters. And if we have really large images, and I don't have to give you more examples. So I think we need to better understand when our algorithms perform well and when they don't perform well. We won't really be able to get one algorithm that performs well across all problems. And then otherwise, I would say that this comes back to, there are, though, I think some hyperparameters we could remove and start performing better. So for example, right now, maybe it's hard to pick one step size across all these environments. But if on the other hand, we had step size adaptation algorithms that you have to pick an initial step size, you start at some step size, but over time, the step size adjusts to one that works well for that problem. That initial step size might make learning slower or fast in the beginning, but it doesn't prevent you from learning. So I really want us to push towards hyperparameters that you have to initialize, but that initialization washes away over time, and the agent can start performing well eventually. It may make learning faster, slower in the beginning, but eventually it's performing fine, regardless of exactly what that initial hyperparameter was.
Yeah, okay, thank you.
Ma'am, I had a question. So, as the seeds are highly dependent on the underlying random number generator, so can we suppose swap that for a quasi-randomness where we have more control on the discrepancy set?
Somehow it was a little muffled. Maybe could you repeat the question?
As the seeds are depending on the internal pseudo-random generator, so can we use instead of quasi-randomness something like Sobol or something for the quasi-randomness, so where we have control over the discrepancy set of the random number generator, and would that produce better results?
Okay, so I think you're saying that if we use a different random number generator, would that produce different results? But maybe you could tell me more why you think it might produce better results.
As so this dependency on the seeds is a huge parameter, importance for, as it changes the final output of many of these benchmark algorithms. So suppose if we are using some other randomness, so we can have a more control over how the numbers are sampled from some set.
Okay, so are you saying that instead of a lab picking seeds 1 to 5 and then overfitting or thinking certain results happen from 1 to 5, if there was a different generic strategy to pick seeds so you couldn't get overfitting to some subset of the seeds?
Yes, more or less.
I think there's something definitely nice about not having as much control about how exactly our algorithms run. Like if there was a way we could someone else runs your algorithm and they do things like randomize which seeds are chosen and so on, I think would be a very nice thing to do. So I agree with that. One other thing I suppose we could do is randomize the seeds ourselves so that we're not always picking the same seeds. But at the same time, then now we're just adding variation so that we also don't trick ourselves. So I think there could be different ways to control for that variation without intentionally adding extra stochasticity.
Thank you, ma'am.
Hi, Professor. I have a question. So there is a lot of code base available in the community platforms like say GitHub. So do you think having a open source curated repositories that can help in standardizing the oral experiments and set a benchmark?
Right. Yeah. If those open source platforms were to, sorry, were you saying more?
Yeah. See, there is a huge set of code available in platforms like GitHub. And do you think they have a role in helping in standardizing and creating the benchmarks for oral experiment practices?
Yeah, I mean, they definitely have a role in how we run our experiments. And maybe you're saying something more here. Are you saying that they should be playing a larger role, or?
I'm asking, do you think they have an opportunity to bringing in such standardization in the practices?
Oh yeah, definitely. I think if those packages that are widely used, like stable baselines and all those, had examples of ways that they thought were clever ways to do experiments, ones that you could do experiments with fewer runs but still make interesting conclusions, would have a really big impact on how we run our experiments. And again, here I'm not saying I know how to run experiments well. So if in general more people were to propose clever ways to run experiments in those packages, that would be very helpful for everyone.
Okay, yeah, thanks.
All right, so maybe I'll pose the last question. So you mentioned about online RL. I wanted to know how common is it to deploy RL algorithms in the online setting? What are the fears of running them in the online setting? And what do you think should be features of RL algorithms so that they, practitioners would be, more ready to, use such algorithms in the online setting? Can you please comment on that?
Yeah, sure. Okay, when is RL actually used online? So I'll say that my group has been using RL online. Like we've actually deployed RL algorithms on real water treatment facilities. They're controlling chemical dosing online whilst the plant is running. And in my opinion, actually, it's safer, at least for our application, to deploy an online RL algorithm rather than, for example, an offline one where you trained first, then deployed a fixed policy. Because a fixed policy is brittle. It's not adapting to things as they change. And conditions in these facilities change actually quite a lot. Water changes, filters get gunked up. So it's better to have essentially a feedback controller, something that's always taking feedback and updating its policy. So my opinion is online RL is safer. An online RL solution is safer than an offline RL solution for our problem setting. I'm not in healthcare, so I'm not going to make any strong claims about healthcare. And then what do we actually? Sorry, go ahead.
No, in one of your plots, you had shown that the performance, in particular one run of your DQN, right, went up and down, right? And perhaps my understanding of that was on certain time instances, you had a good policy, then you went to a bad policy, and then you came back to a good policy. I don't know how, that would be appreciated in online setting, right? So that was one of my concerns. Like, when you run it in online setting, how do you ensure that your policy doesn't, for intermediate time steps, become bad, right?
Yeah, no, I'm actually 100% with you. I think this is one of the reasons RL algorithms are not that widely used, because we see results that are of that type. I will say for our problem setting, it's inherently actually sounds like a simpler problem. It's one where you have very clear guardrails. You can do quite a bit of exploration in those guardrails. We have historical data to initialize our agents, so it's not starting from scratch. And we have found that some simpler RL algorithms can actually perform quite well in that scenario, and we don't see this weird behavior. We actually see it generally monotonically improving. But I wouldn't personally take RL algorithms right now and put them on systems where things can explode, or inside auto driving, like automatically driving cars or anything like that. So I think for some problem settings now, we can get some of our simpler RL algorithms to work. If we want them to start being applied more broadly, we do need to start addressing these issues in our RL algorithms.
Can you give some examples of these online RL algorithms that you're using?
I guess actually right now I can't talk about that because it's part of this company that I have started called RL Core Technologies.
Okay.
But we are going to be releasing some papers, so you'll get to hear about it then.
Okay, thank you. So with this, let's end today's talk. So let's give a big round of applause for Martha White. Thank you, Professor Martha White, for this very insightful talk.
Thank you, everyone.
Thank you.
Okay, I guess I'll sign off. Thank you, everyone. It was a pleasure to be here. Thanks for all your great questions.
Thank you. So we are now going to have the last talk of the morning session. I have the honor and pleasure of introducing one of the upcoming talents in the Indian research arena, Professor Avik Ghosh. He's an assistant professor in the Department of Computer Science and Engineering and an associate faculty member at the Center for Machine Intelligence and Data Science at the Indian Institute of Technology, Bombay. He works in theoretical machine learning with a focus on large-scale optimization in federated learning, sequential learning in reinforcement learning, and multi-arm bandits. Previously, he was a postdoc at the University of California, San Diego, and he did his PhD from the University of California, Berkeley. So with this, let me request Professor Avishek Ghosh to give his talk.
Okay. Thank you everyone for attending this session. Is it audible? Okay, some technical issues. It's working, right? Okay, so let's get started. This is the talk before lunch, so I would like to keep it short. So I will talk about structured multi-agent multi-arm bandits. So there are two keywords here. One is structured, and the second thing is multi-agent systems, right? So let's get started. So I should say that multi-agent multi-arm bandit is an active area of research, and take any recommendation systems like Amazon, Netflix, Spotify. So they deploy multi-agent RL framework, and also take games like economic market. So you will see applications of multi-agent RL everywhere. I don't have to motivate multi-agent RL to this audience. So this talk is divided in two parts. In the first part, I will talk about what's called a federated bandits setup, and there we will leverage a structure called clustering. And here we will see collaboration across different agents in the system. Okay, so this is a collaborative framework among multiple agents. And in the next hub, I'll talk about competition across agents. So you have multiple agents, they're competing. So this framework is popularly known as markets and bandits. So here we will leverage what's known as the linear contextual structure. So I'll explain it more in the second half. Okay, so let's get started with the first topic. So this is kind of a rewriting of what I just said. In the first half, we will focus on clustering, and the second half, we will focus on this linear contextual structure in the collaborative and the competitive environment, respectively. Okay, so let's get started with federated bandits. So in a federated bandits, you have n agents trying to learn something on their own in a sequential manner, and you have one central learner. Okay, and the caveat here is that so these agents, so they cannot talk to one another. Okay, so they can only communicate through the central learner. So this has received a lot of attention in the last few years because this is highly decentralized. So you can think of a very large system, and you can deploy this kind of topology there as well. So here in this talk, we will talk about kind of heterogeneity across different sequential agents, and in particular, we take the canonical example of clustering. Okay, so let's talk about the formulation. So we have n agents. Think of n as very large, and we have m clusters. Okay. So all the agents in one cluster, they are solving a single instance of a bandit problem. So there are m bandit problems with n users, and the clustering map, this script m, is not known a priori. Obviously, if this is known, then you would have clustered first and then look at each cluster. There is no heterogeneity. And we also assume that the set of arms, k, is common across all the agents, across all bandits. And just for a notation, so for each arm k and each bandit small m, so if you pull the arm, you get a reward. So we assume that the reward is distributed as one sub-Gaussian, which is a standard assumption, with unknown mean of mu m comma k. Okay, we will use this notation throughout. And the goal here is to find the best arm for all the bandits. Okay, so since I said that all the agents in one cluster, they share the same bandit instance. So if I can find the best arm for all m bandits, it's equivalent to say that I'm finding the best arm for all the agents as well. Okay, so we care about two key factors here. One is the sample complexity, meaning the number of pools to identify these best arms, and the second thing is the communication cost. So remember that this is a federated setup, so you have different users and different agents and one learner. So there has to be some communication from this agent to the server, right? So usually in federated systems, this communication is done through internet bandwidth or something like that, which is a resource constraint thing. So it's a good idea to have algorithms which have low communication cost. So this is also one of our concern on top of this random pools. So in this talk, I will not discuss more on the communication cost. I will give little hints about it, but we'll mostly focus on the sample complexity, the number of pools. Okay, so needless to say that clustering in multi-arm bandit has a very rich literature, starting from work of Gentile back in 2014. I did some work as well. Arithra is here somewhere, I saw him. Yeah, he did some work back 3 years back. There are recent works as well. So just want to identify where we stand with respect to all these works. So all these classical works by Gentile, so they focus on a structured bandit called clustered linear bandits, and they focus on regret minimization. On the other hand, this Srinivas et al. So they define what's called a federated based arm in in some setting, and they're mostly focused on finding the best arm in that federated setting. Also, in this recent work by Chawla, I think Professor Shakotai was also there. So they actually use a gossip type algorithm for different agents in a graph with side information. So in our case, we don't have any side information, and our kind of graph is fixed. We have a star graph, and we don't use kind of this gossip type algorithm. We have this one center that fuses all the information, and we actually propose algorithms which give you kind of sample complexity which are near optimal in some regimes. It will be clear when I explain it. Okay, so throughout this first section, we will assume some separation. So you can identify that this is like a clustering problem, right? So every clustering problem should have at least some notion of separation. So this is just saying that if you have two bandits, if you the laser works. Okay, is it working? So if you have two bandits A and B with best arms, let's say K star A and K star B. So basically says that on a bandit B where K star B is optimal, K star A will perform at least delta watts. Okay, so I should apologize that throughout this talk I have changed this notation to eta, but I forgot to change the first instance. So think of delta as eta. Okay, so this is just a separation across different bandits. Okay, so what is it that we want? We are given a bandit instance with n agents M clusters K arms, and this clustering mapping as well as the reward distribution. So we take a parameter, let's say any parameter delta, and for an algorithm A, assume that the output, meaning that the best arm it outputs for n agents is O1 to On in some T number of pools. Okay, so we say that this algorithm is delta probably correct or delta PC if the error, meaning that OI is not equal to the best arm for that corresponding bandit for all the agents, is less than equal to delta. So that is the definition. Okay, so we'll propose several algorithms which will be delta PC. Okay, any issues with the definition of the algorithm? So we want to do this job in finite time, obviously, and we want to make correct predictions about the best arm. Okay, so we'll look at two algorithms. So the first algorithm is clustering and then best arm identification. So as the name suggests, this is a two-phase algorithm. So we will do clustering first, and then we will do best arm identification. So let's look at the clustering phase. This is not how you prepare slides, but it was a last-minute thing, so I kind of did this. Okay, so let me go through what is the first phase. So the first phase is the clustering phase. So as you can see that so you have input as this error parameter delta and the separation eta. So all agents will run what's known as the successive elimination. So successive elimination is a canonical algorithm to find the best arm. So it basically samples the arms given to you in a set, and so successive elimination is given in this subroutine. So just overall idea is successive elimination will output a set which will contain the best arm. So that's successive elimination in one round. Okay, so it is typically used to find the best arm. So if you run successive elimination for many rounds, the set you end up with will have only the best arm. So that's the idea. Okay, so all agents will run successive elimination algorithm on the set of all arms for some given error probability and given number of rounds. Capital R is the number of rounds. And they will communicate this set of arms SI. And so when you are performing successive elimination, you are sampling the arms, right? So when you're sampling the arms, you can construct the estimate of the mean. Okay, so if you collect all those estimates, you get this vector mu hat I. So it will communicate the set of arms and this mu hat I back to the server. Okay. So I have chosen this number of rounds and the error probability in such a way that this in this SI for agent I, so SI will contain the best arm for agent I. Okay. So it will obviously contain the best other arms, but it will contain the best arm for agent I. Okay. So this is done. Now at the center will actually create a graph. Okay. And so it collects any two agents. Oh, okay. Yeah.
M bandits.
So the M bandits. M is the number of clusters.
Hello?
Capital
Yes.
M is the number
so
of
my
clusters.
question is, I'm a bit confused between bandits and arms. So I see K here is the number of arms, but
Yeah.
where's M, right? You had M.
So all
number
the
of
bandits will share the same set of arms. Okay, so there is a set of arms and it is shared across all the bandits. Okay. So
what are the users then? So
every user will belong to one of the clusters. It will have a best arm among those K arms. So for different users in different clusters, they will have.
So users are identified with bandits or no? Users and bandits are different.
So users or bandits are different. So in this notation, bandits mean a particular cluster. So there small m bandits mean small m clusters. Okay, and user may lie in one of these m. So if this is confusing,
so the M bandits or M clusters of M times K bandits.
So capital A.
Okay, so sorry, M times. Yes, so I'm still confused. Sorry, but
Okay,
maybe
so
it's my problem. Sorry.
No. So let me try to explain it better. So there are n agents, okay, and there are m clusters. So forget bandits. So there are m clusters.
So you want to cluster agents into. So you want to cluster agents into clusters, right?
Yes.
Okay.
And
M clusters. M clusters.
So I'm just saying this word cluster as bandits. So if you're confused about that, I will use the word cluster from now on. No bandits.
Okay, so clusters, and each agent has its own bandit. Each agent solves its own bandit.
Yes.
Okay.
Yes.
Thank you.
And so the cluster is identified by the best arm. So two clusters will have different best arms.
Okay, but in the same cluster, it's identical, statistically identical.
Cluster, they have the same best arm.
Okay.
So that is how we are defining clusters.
Okay, thank you. Now it's clear.
Okay, great. So yeah, so after the first round, we have this SI for all the agents. So now the center will construct a graph, and it will just take these pairwise differences for the kth arm. Okay. So for all k in Si union Sj, so it will create a link between I and j if the difference is small. Otherwise, it will not create a link. So it's as simple as it can be. So I have all the empirical data, and then I'm just creating this cluster based on whether those empirical estimates are close or not. That's all. Okay. So as I was saying, so I have put these numbers, this number of rounds as well as the error probability in such a way that for any two agents who are in the same cluster, meaning they're learning the same bandit, then this difference is less than or equal to eta over 2. And if they are learning different bandits, then this difference will be bigger than eta over 2 with high probability. So this is just, yeah. Yeah. So
K,
yes, K is greater than M. Okay. So yeah, this is just a very simple instance. So I mean, all the number of rounds are set in such a way that this graph outputs exactly m number of connected components. So you should take those as your clusters. Okay. This is a very naive algorithm in that sense. So the first phase is done, the clustering phase. So now in the second phase, I will just pick one agent from each cluster, and I will run successive elimination until and unless that agent finds its best arm. Okay, so that's the second phase. So now our job is done. First you cluster, you use these empirical averages to construct these connected components, and then you treat that as your cluster and pick one agent and just run successive elimination. So that's as simple as it can be. Okay, so we show that under separation assumption, it's not difficult to see that this algorithm is delta PC. And we also give sample complexity guarantees. So sample complexity is divided into two parts. So T1 plus T2. So T1 is the sample complexity from the first round of clustering. So as you can see, so if you just ignore all these log components, so just look at this max of two things. So so it actually depends on the gap, the suboptimality gap, as well as the separation. Okay, so we actually pose it in such a way, and we also have the assumption that the clusters are separated. So it suffices to take the max of this gap as well as the separation, and we can actually prove that the first round sample complexity is that quantity. Okay, and you can see that since all the agents need to do it, we have to sum over all the agents. And in the second round, we can just take one agent from each cluster representative. So it's a summation over only the number of clusters M. Okay. Okay. So now let's compare this with the naive scheme, which actually ignores all the clustering structure.
Sir, I have a basic question. So you said that clusters are basically based on the best arm that each agent chooses, right? So then, what second phase you again have a best arm identification? What is that like? So
in the first phase, you don't find the exact best arm, right? So you don't run it for that many iterations. You find a set which contains the best arm. So now from that, you have to go to the best arm. So if you look at in the second phase, we run the successive elimination with the number of rounds equal to infinity. So until and unless you find the best arm, obviously it won't run up to infinity. It will truncate when you get the best arm. So you can get that. Okay, good. Please ask questions. Yeah.
So it seems like in your phase one, the knowledge of eta is critical, right? Because unless you know eta, you don't know.
Yeah. So as I said, the algorithm needs the knowledge of separation or any lower bound of it as an input. So this is a shortcoming. Yeah.
I see. So is there any hope of doing some kind of adaptive clustering where you start with some gas of eta?
I'll talk about that. So we can keep on we can start with a big eta.
And then keep halving it or something.
Keep halving it, yeah. So in this particular instance, we don't do that, but that's definitely one thing that can be done, or it's in the process. We do that.
And another question I had is that for your phase two, can you show that within each cluster, each agent benefits by exchanging information, in the sense that within each cluster you'll have n over k agents, right?
Yeah. So we will see all those benefits. It will come in comparison. Okay. So one thing that I kind of omitted. So in the second phase, so what is the advantage of doing all the successive elimination in the first phase? So you get all the set of arms which contains the best arm, right? So in the second phase, you don't have to run successive elimination over the set of all arms. You can use whatever set it learned from the first time, and you can use it there. Okay, so now let's answer Arithra's question. So suppose we have sort of a symmetric system, balanced cluster structure. So assume the size of each cluster is n over m. So if we were to ignore the clustering structure, so any naive algorithm would do what? So it will take all the arms, right, and it will try to find the best arm. So we all know that the sample complexity will be k over the minimum gap square, something like that, right? So if you have k arms, the minimum gap is some delta. So you need that many pools to find the best arm if things are sub-Gaussian. So for all n agents, so the sample complexity will be something like this. So think of this delta bar as sort of an average gap. So on the other hand, in our case, so we actually leverage the separation condition. Since the clusters are separated, so that's a huge side information. So leveraging that, it turns out that instead of just looking at the suboptimality gap, we can look at the max of suboptimality gap and separation. So in many cases, the separation is much bigger than the gap, because we can have a bandit instance with gap very close to 0. Okay, so in those cases, so our algorithm will be beneficial in terms of the number of pools, and also as Aritra said, the number of pools in terms of so we actually get the benefit from clustering. So from nk, we can bring it down to mk, because we are not sampling all the agents, we are sampling one agent per cluster. That's all. Okay, so we propose a second algorithm. So let's reverse the sequence. So here we actually do the clustering first, and then so here we do the base term identification first, and then we do the clustering. Okay, so just let's have a look at this algorithm. So in the first phase of this algorithm, so you have n agents. So you are picking agents uniformly at random. Okay, think of without replacement. You are picking agents uniformly at random, and so first of all, there are m clusters, right? So how many times do I need to pick agents so that I can see at least one agent from all the m clusters? So can anyone answer this? So you have m clusters, you are picking agents uniformly at random without replacement. So how many times do I need to do this so that I can see at least one agent from each, at least one agent from all the clusters? Anyone? So this is exactly the coupon collector problem we study in probability, right? So the answer is of the order m log m. Okay? Okay, so we'll come to that. So the idea is we will sample agents uniformly at random, and then we will run successive elimination on that sampled agent for some time. Okay? So now these number of iterations and all are designed in such a way that this Si will contain the best arm for agent I, and Si will not contain the best arm from other clusters. So it will only contain the best arm of the cluster where agent I lies. Okay? Okay, so let's run through this algorithm. So we'll start with this S equals to a null set. So this quantity is not satisfied. So if you pick agent I, so then you construct Si, it will contain the best arm. So you will run successive elimination on agent I for infinite number of steps, meaning that you will find the best arm for agent I. Okay? And you actually put this best arm in the set S. So as you proceed, this set S will contain all the best arms from m different clusters. Okay? And so this condition basically checks that if that particular cluster, if the best arm for that particular cluster has already been identified or not. If yes, you don't have to do anything. If not, you find the best arm for that cluster. Okay, so very simple algorithm. So, and I will actually remove that agent from this set of all the agents A. So at the end of first phase, so the cardinality of S is m. It contains only the best arms from m clusters, right? And the number of pools that I need, and the number of times that I need to sample agent is of the order m log m. That comes from the coupon collector problem. Good. So now in the second phase, so you are in a good shape, right? So you have the set containing all the arms, all the best arms. So you can just run successive elimination over that. So this is successive elimination over the set that contains all the best arms. Okay? And you can run it up to infinity, meaning that whenever it stops, for all the other agents. So you are running this for all the other n minus m log m number of agents. So this number of agents can be large, but they are sampling from a set which only has cardinality m instead of k, which can be much larger. Okay? So this is where the advantage lies. So this is not clustering per se, but it's kind of finding all the agents which share the same arm and put it in a bag. That's it. Okay? Any questions about this? Yeah, as I said, this SI contains the best arm for agent I, and it will not contain the best arm corresponding to any other clusters. And we will run successive elimination on set S. Okay, so we can analyze the sample complexity for this particular algorithm. And as I said, this should remind you of coupon collector. This m log m kind of pops up. So the first term comes from this initial successive elimination, and this term will come from the successive elimination of finding the best arm for that particular agent. Okay, and this term is actually the sample complexity for the second round. So you have n minus m log m number of agents. So they are trying to find the best arm. So the number of arms will be m, and the separation is already there. So this is same as the naive algorithm. The only difference is that instead of k arms, you have m arms. And m, think of m as something very small. Think of m as constant. The number of cluster, assumption that the number of cluster is constant is not a very bad assumption. So the sample complexity is much lower. So that's what I'm trying to say here. Okay, so then look at the comparison. Let's look at the comparison between the two algorithms I just proposed, and think of separation is reasonably large. When I say reasonably large, it's not like huge, but it's larger than the banded gaps, let's say. So then if I look at the sample complexity of both the algorithms, so the first term is the same. So for the first algorithm CLBAI, the second term scales with n times k. N is the number of agents, k is the number of arms. Both of them can be much larger, right? On the other hand, this quantity scales like n times m, which can be much smaller. Okay? So think of n as very large, k as somewhere in between, and m as a constant. M is very small, number of clusters. Okay? So it's obvious that this BAICL, best term identification, using coupon collector kind of argument and then find the best arm is better choice given these two. Okay? Yeah, so this is exactly what I said. So if m is much smaller than n times k, then the best term identification first algorithm performs much better. But on the other hand, so the CLBAI has some advantages. So you can run that algorithm in parallel, which can be advantageous sometimes, but let's not talk about that. And one aspect that I did not talk about is the communication efficiency, the amount of communication you need from the agent to the learner. So it turns out that this BAICL, the better algorithm in terms of sample complexity, is also communication efficient. So over and all, so we started with a naive algorithm, sort of, then we kind of improved it. Okay? So we can make further improvement. So in the separation assumption, we said that we fixed the cluster, and we said that the best arms across two cluster agents will perform some eta words. So here we fix the best arm. Suppose you take the ith cluster, fix the best arm k star I, right? And now take two clusters, I and j. So just says that this K-star I, this cluster I, whose best arm is K-star I, is at least eta 1 times beta. That's all. So this quantity is positive, so there is no need for absolute value. Okay. So in the previous assumption, so we fixed this bandit, this clustering, and looked at different arms. So here we fix the arm and look at different bandit instance. Okay, different clusters. That's all. So it's similar. The assumption is similar. It turns out that using this assumption, we can actually improve this BICL algorithm to BICL++, with some improvement in sample complexity. Okay, so that improvement is not order-wise, but in some cases, in experiment, I will show that this is very close to the optimal complexity that you can get. So let's talk about optimality, and for that, we need to look at the lower bound. So let's first fix our class of problem instances. So we consider the class of problems where these two, both the separation across clusters and the separation across arms, both of them hold. Okay, and also let's assume that the separation parameters are like eta are the same. Okay, otherwise we can just take the minimum. It's not a big deal. And we also assume that the reward is sampled from Gaussian distribution. Okay, so earlier one was sub-Gaussian. For the lower bound, we need Gaussian. So people who work in lower bounds and all, they know the reason. But okay. So we can show that for any algorithm for this class of problems, there exists a problem instance such that the expected number of pools is at least this max of m times k and n times log 1 over delta over eta square. Okay, so no matter how good your algorithm is, so for the problem instances that satisfy separation 1 and 2, you need to pull at least this many arms in order to find the best arm for all the agents. Okay, and the proof of this is quite simple. So we use this kind of measures change inequality. Let's look at the KL divergence between two instances. So we define an instance and then a perturbed instance and then use some standard measure change argument. So I can talk about it maybe after the talk, after this session. Okay, so now the important thing is, so this BICL algorithm that we proposed, it seems like a very naive algorithm. It turns out that in some cases, under some regime, this algorithm is near optimal. Okay, so we first actually apply this BICL algorithm on this instance over which we prove the lower bound. Okay, so we got a sample complexity given by this, and we compared this with the lower bound, with the terms in the lower bound. So we see that this mk appearing here also appears in the lower bound, and the n term also appears in the lower bound. So we have all the terms here that appears in the lower bound, but we also have this capital M which was absent in the lower bound. Okay, so this is sort of capital M times more sample complexity than what the lower bound suggests. Okay, so in the case where this M is a constant, so we can say that the number of pools is actually order-wise minimax optimal. Okay, and so the improvement is also order-wise minimax optimal. So a simple algorithm can give you very strong result in terms of sample complexity. So that's the takeaway. Okay, so we have also done some simulations. So there is a mistake here. So the leveling is not correct. So let's look at this plot. So this blue line will be the naive algorithm, and then this is the performance of all the algorithms that we have described, and the lower bound. We can see that this BICL and its improvements, the performance is very close to the lower bound. And the first algorithm, which is sort of an improvement over naive algorithm, it's not that intelligent, sort of naive-ish. So its performance is we have this clustered federated setting, and we looked at several algorithms, and we also looked at some lower minimax lower bound and talked about some optimality of our proposed schemes. And this is a joint work with BTech student in the electrical engineering department of IIT Bombay, Yash, and with Professor Nikhil, who is also faculty in EE, IIT Bombay. So we will soon archive this, so stay tuned. So any questions on this? So now we will switch to the next part.
Why you chose successive elimination as the algorithm for?
Yeah, that's a good question. We could have chosen other schemes. The student was more into successive elimination, I guess.
Because when you give the lower bounds, you won't be able to get optimality. Maybe track and stop you can.
Track and stop you can, but order-wise, I don't think it will be that much different. So everything is order-wise, so we can't make any.
No, I think my experience with the bandit reviewers is that when I do successive elimination, that gives them ammunition, the reviewers, to come back at me. If I do track and stop and match the constants,
yeah, we have this similar
people don't seem to complain. This is personal experience. Yeah.
Yeah, I mean, we could have used, but I think one reason why we use successive elimination is because of its simplicity. So we are massaging successive elimination in several ways. So we are changing the number of rounds, we're changing the set, we're changing many other things, the probability. There are many tuning knobs in successive elimination. So that is one answer to your question. But maybe in other algorithms, there will be other tuning knobs.
Yeah. Yeah. Also, I didn't understand the MS theta of one business. So
So this is just saying that if the number of clusters is constant, is not that big, then the sample complexity of BAICL is matching the lower bound order-wise.
Yeah. So if you have a large number of clusters and
if you have a large number of clusters, then this is not optimal at all. Yeah.
Okay. Yeah.
Then it actually increases by a factor of m in theory, but not that much in experiments.
So you think the lower bound is the lower bound is suboptimal, or the upper bound is suboptimal?
The upper bound, definitely.
Okay. Yeah. Okay. Thanks.
Thanks. Okay, so let's change gears and let's talk about the second setup. Don't have that much time. So here we have different agents and they are kind of competing. So this is a competitive setup, and this is known as markets and bandits. So I'm just defining what a matching market problem is. So this is a traditional market. So in traditional market, there are no preferences, nothing. I don't know if this is even called a traditional market. But anyway, so if there are no preferences, there are no resource crunch, nothing, then you get what you want. Okay, but life is not that easy. So in a practical situation, so you will have different agents, and then you will have different resources. Here the agents are kind of students asking for college admissions, and then there are these colleges who provide admission. Okay, so suppose so there's a constraint that each college will take only one candidate. Okay, suppose this is not very practical for colleges, but let's say like students are competing to get into let's say Professor Burkhart's lab. Okay, and he will take only one student.
I never had a lab.
I mean, group, let's say, and he will only take one student. So there will be competition, okay, and there is obviously. Okay, so in order to model these kind of systems, we use what's called a two-sided matching market, where each agent will have a preference over the schools or the colleges, and each college will also have a preference. Okay, so some college may be looking for someone good in academics, and some college may be looking for someone good in sports, maybe just for this year or something, and and similarly, each student will have some preference over the college. Okay, so we define a matching as an injective map, many-to-one map, from this set of players to set of arms. So this side will be called players, left side, the right side will be called arms. So matching is denoted as in injective mapping from players to arms. Okay, so now our goal is to find what's called a stable matching for all the agents. Okay, so now let's look at the stable matching for this particular example. So note that for student 1 and student 2, both of them actually prefer this orange school, okay? But orange school actually prefers student 2 instead of student 1, okay? So if I were to put this map, so this map is not stable because this college and this student, they were both off by not using this map, okay? The student will be beneficial as well as the college. So these kind of pairs are called blocking pair, and if a map, if there exists no blocking pair for an injective map, we call that match a stable match, okay? So okay, so just to rewrite the same framework without all the fancy pictures. So we have an agent side, we have the arm side, and there are and the goal is to find a stable match which will be a bipartite matching in presence of competition. So there is a resource crunch. So it received a lot of interest in the last 5-6 years, and it has a lot of motivation. I will talk about the motivation. So like in labor markets like TaskRabbit, Upwork, Amazon Mechanical Turk. So back in the days, medical interns and residents were matched to their hospitals using this kind of matching. And so it's a generic way to kind of match the demand and the supply side. Yeah, as I said, each agent will have preference over arms, and each arms will have preference over agents. So in some cases, so it's very difficult to actually solve the problem when both the set of preferences are unknown. Yeah, one second. And in fact, this is an open problem. So if you don't assume anything on this preference structure, so learning in the presence of both this unknown agent is still kind of an open question. So what people do is the following. So they assume that the ranking in one side is known, is given to you, maybe based on some historical data, and you learn the ranking in the other side. Okay. So typically it is assumed that the ranking of the agents is known to the arm. So each arm will know the ranking of the agents. Okay. So in the university example, each university will know the ranking of the students. Maybe that's not a good motivation, but this is something people assume. Yes, your question.
So it's not a question per se, but the motivation that you started with in university setup. So I think another scenario, let's say in colleges we have a TA, every faculty is given a TA. So there, as you say, one faculty can be given one TA, so we need to find an assignment. So can we use this framework to solve that problem?
I mean, that's obviously an example that fits in the situation. Okay. Now, if you'll use this algorithm to solve that problem, it's up to you. But this fits in the model. Yeah. Okay. That will be an overkill, but yeah. Okay. So, as I said, like different applications where you are trying to match this agents to arms is an instance of markets and bandits. And so if the preferences, so what is the challenge here? So do I have that? One second. Right, so now I should ask you this question. So suppose these preferences are known. Okay, so there is nothing to learn. Suppose these preferences are known. Then can you solve this problem? Yes, no, maybe? So if the preferences are known, then there are classical algorithms to output a stable match. So this classical algorithm called Gill-Shapley. The name of the algorithm is deferred acceptance. So you might have heard of what's called a stable marriage problem. So these are all instances of applying this Gill-Shapley algorithm or the deferred acceptance. So the idea is if these things are known, then it becomes a very easy problem. But the caveat is that we don't know the preference ranking, and we're trying to learn that over time. Okay, so that is the challenge here. Okay, so we can model this kind of supply versus demand framework as multi-arm bandit. So we consider this n agents and k arms. Okay, and we assume that when agent I pulls arm j, it receives a reward of mu ij, and the agent's preference is actually dependent on ordering of this arm means. Okay, so agent I will, so if mu I1 is bigger than mu I2, agent 1 will say that I prefer arm 1 over arm 2. That's it. So each agent is solving a multi-arm bandit problem, but the issue is that, so there are multiple agents who are trying to solve a multi-arm bandit problem simultaneously, and they're trying to grab the same arm, let's say. Okay, and so there will be competition, and we need to resolve the conflict. So it's one way to resolve the conflict is to have this kind of assumption. So if more than one agents pull the same arm, then the reward will be given to the agent preferred by the arm. Okay, so this each arm will have a preference ordering over all the agents. So if there are 10 agents pulling arm 1, based on arm 1's preference, so suppose arm 1 prefers agent 2, so agent 2 will get the reward, and everyone else will get a deterministic 0 reward. Okay, so usually in multi-arm bandits, if there is collision, everyone gets 0. So that is kind of the usual setup. But here, so this the competition is rewarded by this preference structure. Okay, good. So what we study is a contextual markets. So for each agent, there exists a latent parameter, and at each round, so agent I will have an access to a feature vector, and the arm mean is parameterized by this latent vector. So if people know contextual bandits or linear bandits, you can directly relate to this. So this is nothing but linear contextual bandit. So we model this framework with features and latent parameters in a linear way. Okay. So theta is fixed across all arms. As I said, it's quite popular in bandits. Started from the paper by Chu et al. In 2011. This paper by Yasin Abbasi Yatkori in 2016 that gives you like very strong near optimal algorithm to solve this kind of problem. So yeah, usually, so this linear structure makes sense when the number of arms is much bigger than the number of agents, but it doesn't have to be. So it's always good to study kind of a structured problem to understand the problem a little better. So if you want motivation, this is a motivation, but apart from this motivation, if we can study the effect of feature, albeit in a linear way, there's no harm in that. Okay. So now we define what's called an environment. So at every time you are seeing these feature vectors, and we can define an environment based on that. So note that this feature vector actually prescribes the mean, and based on this mean, you are defining the preference. Okay. So we define an environment. So we define an environment where these preferences over agents and arms remain the same. So if you have two different environments, then these preference vectors will be different. So that is how we are defining an environment. Okay, for two different environments, these preference vectors will be different. And for intuition, so this is just from Amazon Mechanical Turk. So you can think of environment as different type of jobs. Okay, so maybe someone is very efficient in kind of pairwise ranking. If you give like two things to kind of rank, which one is better than other, it's very good. Is not good at kind of rating something between 0 to 10. Okay, so just think of different type of tasks as your different environments. So these preferences and all will depend on the type of task, and different preference is equivalent to different environments. Okay. So as I said, so we also work in this one-sided learning. So we assume that these arms are aware of their preferences, but the agents do not know, and they need to learn these preferences. And each environment has its own preference. So it needs to learn the preference for all the environments. Okay, so we assume that the number of environment is kind of finite. So there are capital E number of environments. So we need to learn all these capital E environments. And you can pose this as a dynamic markets and bandits problem, because based on these features are time dependent, the preferences are time dependent, so the environment changes with time, right? So this is an instance of non-stationary multi-agent problem, and also you can, in fancy words, you can call it as a dynamic matching market as well, because things are changing with time. Okay, so we need to define a regret. So for a given environment ET, we can define M star as the best arm possible, and your algorithm is giving you MI. So just the difference in mean can be characterized as a regret. So we want to kind of minimize the expected regret over T rounds. It's a very usual definition of regret in multi-arm bandits. So we will use algorithms very similar to explore and then commit, and this is by Kong et al. In 23. So basically we collect samples from different arms, and we construct this LCB and UCB indices for the arms, and we say that arm 1 is better than arm 2 if the LCB of arm 1 is better than the UCB of arm 2. So every arm you construct the confidence interval. So you wait for them to be non-overlapping. So if LCB is better than the UCB, we say that I prefer this arm. Okay, and yeah, so we need to collect samples in a particular way. It's not that important. So what do we do? So let's start with a simple case where there's one environment. So the ranking is not changing. So this problem is just collecting samples and infer theta. Right? Because there is no environment, nothing, you don't have to identify which environment you are in. So this is just a simple instance of solving the multi-arm bandit problem with this linear structure, and your job is to estimate this theta. And we know how to do it because we know how to solve a linear bandits problem, a contextual bandit problem. Right? So we construct this confidence ellipsoid for theta, then we project it onto the feature, and this awful algorithm by Yatkuri et al. Gives you exactly what needs to be done. Okay, so they actually show it without competition and all these things, but we need to incorporate competition and other things. That's a different story. Okay, so in order to make a distinction, in order to kind of ensure that these confidence intervals actually shrink, we often require some assumption on these features. Okay, and this assumption may come as some spectral property of the vector constructed by the features. Okay, so just some lower bound kind of assumptions. I don't have time to go through the details. So what do we do? So if the environment is not changing, then the problem is not at all interesting, because it's just solving the problem with this linear structure. And by this point, we know how to handle all this online linear regression with parameter theta. So it's not a particularly interesting problem. But if you do this exercise, you get a regret of log t over the gap square, and the dependence on d is d square. So I should mention that the dependence on t and delta, these are optimal, but d square is not. So ideally it should have d, but this is suboptimal in terms of that. Okay, so this is not kind of super interesting. This setup is super interesting, where you don't know the environment where you are in. Okay, so think of this all these latent variable modeling kind of problems. So think of the different kind of environments as different values that a latent variable can take. Okay, so what it does is the following. So it actually computes a partial ranking. Agent I computes a partial ranking of different arms in the following way. So if LCB of the arm J prime is bigger than UCB, then it prefers that. Otherwise, it is equal. Okay, so it's doing using very few samples. So it may happen that it cannot distinguish between two arms. So it will just put equality there. Okay, so this is what partial ranking does. And for any two partial rankings, we define the inversion pair as the following. So if you take any two arms K and J, so in ranking PR, K is preferred, but in ranking PR prime, J is preferred, and similarly the other way around. Okay, so that is logical and logical or, I guess it's self-explanatory. So what our algorithm does is the following. So it computes what's known as the Kendall-Tau distance, which is the number of inversions in these two preferences. And it actually does the following. So it stores this partial ranking as we go in some set. And at time t, if the partial ranking is PRI of t, so if it finds a ranking, a unique partial rank such that there is no inversion pair, it means that we have identified that environment. Okay, because every environment is connected to this ranking. So the overall story is that you don't have to kind of rank all the arms and all. You can only look for partial ranking, and we can run this kind of very simple technique, which is quite efficient, and use the idea of inversion pair to identify the environment you are in. So now the problem is easy, right? So once you identify the latent structure, then you just go back to the previous stage where the latent structure is known. You can solve this problem. So that's the overall idea. You first learn the environment where you are in, and then solve the problem with the known environment. So if we do that, then we get the regret. It's similar to previous one, and the scaling with respect to the number of environment is linear, which may or may not be a good thing. Anyway. So in conclusion, so we actually talk about contextual matching market. So potentially it can capture a large market with a lot of arms and all. This linear structure often helps, and we give an algorithm which is optimal in terms of the horizon and the gap. And I should say this is most of this work is done by student Satush. He is in IIT Bombay, and also a couple of collaborators, long-term collaborators, Shomo and Abhishek. And this is available in this link, and please do check out, and it's under submission. So with that, I would like to conclude. Thank you.
So we have time for 2 questions.
Hi Abhishek. So for the second part of the talk, if I understand correctly, if your environment continuously changes, then you'll get linear regret, right?
Yeah, so I mean, we assume that the environment is, so the number of environments is finite.
Right.
And so if that is too big and all, then it will impact the regret, and this makes no sense if the number of environment is too big.
But just following on that question, that could it not be that your environment changes, but you have similar environments over time?
So that comes in the definition. So maybe the feature vectors change and all, but maybe the ranking remains
right,
same.
Exactly. Yeah.
So that we call that as same environment, although XITs are different.
I see.
So think of different environments as different bags, clusters.
I see. Okay.
Yeah.
Are you assuming that the theta remains same across environments?
Yes. Yes.
Is that a fair assumption? I'm not entirely clear about that.
So
if the environment changes,
so
why should my underlying latent vector remain the same across environments?
That's a good question. So
because in the end, the environment changing is not impacting you, because it's just coming down to learning theta. Whereas if theta changes, then you'll have to handle drift and what happens and all that. So in the end, irrespective of the environment, if you learn theta well, you're good. Is that the core idea behind the algorithm, or am I missing something?
You need to identify which environment you are in, right? Because there are like K
where
rankings
does that hurt?
So
because
I need to learn. So that comes in the regret definition, right? So at every time there is a true environment, and my performance should be close to that true environment, the mu under the true environment.
But if you learn theta irrespective of the environment, you're playing the same way, right? Is there something environment specific in your
so
algorithm?
these features will depend on the, so these features will change with time, right? Theta fixed. Different environment will have these different features.
No, my hypothetical question as a devil's advocate is like...
No, I understand. Ideally, so there
if
will
theta didn't change, and if I just ignore the change of environments, and if I just do the same thing...
No, if you just learn theta...
if I learn theta, have I solved the problem, or is there something I'm missing?
No. So you need to identify which environment you are in, right?
But if I get the feature vectors, that gives it, right? Or what? Okay, so your arms, whatever you recommend, is not just a function of theta, but also a function of the ranking, which you are learning. Okay, so that's the extra bit.
Yeah. So that actually captures in the regret definition.
Yeah, okay.
Of course, for like improvement, we can think of theta I environment based, but this is just a major draft. This is just a like first attempt.
Yeah. Okay. Thanks.
But that's a good point. I mean, we kind of thought that would be captured in the features and the ranking.
But irrespective of the environment, as a human being, I would.
Yeah, you
would change my preferences. I would change my preferences whether if I'm working
will change. But so think of theta something as kind of connected to the agent. So think of agent's kind of age, where the agent lives, and something like that. So that kind of.
No, to have just one theta across environments.
Yeah, I mean that's kind of the ongoing assumption, but
thanks. Thanks.
So the complexity that you were talking about, we captured that, but not through this theta. But I take your point that theta should also be changed with environment.
Okay, that's probably the next thing. Yeah, thanks.
Okay, maybe in the interest of time, we can have other questions discussed offline. So let us give a big round of applause for Abhishek.
Thank you.
And we would like to, as a token of appreciation, give a small goodie bag to you. Thank you, Abhishek. So we will rejoin at 2 o'clock. The talk at 2 o'clock is again online talk. So please be on time so that we can start early. Thank you.